determine a maximum steady state amplitude of vibration. Maximum steady state amplitude of vibration. There is A part, and B part is maximum dynamic stress in the columns. Maximum dynamic stress in the columns. Full stop. Right on the next line. Weight of girder and machine is 66.75 kilonewton. 66.75 kilonewton. Is like this. Magnet is fixed, other is fixed. The supercritical type of machine exerts a force, f of t, which is given by this equation. Weight of the machine and that of girder is 66.75 kilograms. Height of column is 4.57 meters. The chemistry of the column is 080 centimeters to floor. Section modulus of the column. Area of the column is 100 centimeters. Read the problem once and see what is asked. In the A part, they ask the steady state amplitude. Steady state response is Yp and maximum value of Yp is E, and it is given by this equation f0 upon k, y static into magnification factor. We call this equation 1. And you can say the amplitude of steady state response is given by equation 1. Now collect all the data that is required in this equation. First f0. F of t is f0 sine omega ft. Comparing that, f of t is f0 sine omega ft. So you can say f0 is 890. Omega 5.3 radian per second. Next, capital R is given in the problem directly, 5%. So 5 upon 100, that is 0.01. Next, I have to calculate stiffness of the structure. Okay. Assuming the girder to be infinitely rigid, what is the stiffness of this structure?
EI upon H cube.
Yes,
15 EI upon H.
that is right. Column with fixed base contributes to 12 EI upon H cube, and a column with hinged base 3. So that's how it is 15 EI upon H cube. Take everything in Newton and meter. So 15 is a steel frame, so E is equal to 10 raised to 5 Newton per mm square into 10 raised to 6 Newton per meter square. Because mm square is in denominator. I is given to be 2080 centimeter raised to 4, so 10 raised to minus 8 meter raised to 2 divided by H 4.57 cube. That will give you K. How much it is? How much? No, something is wrong. Please check. Yes, how much it is? Those who are online.
653.786.
How much?
Into 10. 653.786 into 10 to the power of 3.
Okay. It's not 2080. It's 2880.
$905.24.
All right. And 05.24,
24.
one more digit.
3.
3 into
Power of 3.
10 raised
3,
to
sir. 3.
10 raised to 3 Newton per. To find omega, I need mass. That is equal to W upon G. Convert mass in Newton first. Sorry, weight in Newton, and then tell me the mass. Mass is 6807. Reduction of 0.056 kg. Now you can find omega, natural frequency of vibration of this structure, K upon M. Eleven point five three two. 532 radian per second. And now you can get smaller frequency ratio. Forcing frequency omega f upon omega.
0.459, sir. 459.
0.459.
9. Yes.
Okay. And now substituting all these in equation 1, you will get y max. Amplitude of steady state response.
One point two four three
1.243 unit
into 10 to the power of -3, sir.
raised to -3 meters, or you can say 1.243 mm is the maximum deformation y max of both the columns. Is it okay? All right. Now see what is asked in B part. In B part, they asked maximum stress in the column. Now, the column is subject to two forces. One is bending moment, M, and other due to weight of girder and weight of machine, it is subjected to axial force. So in B part, the maximum stress in the column is axial stress plus the bending stress. Is it? In steel structures, we can calculate axial stress as P5 and bending stress is L by Z. I know area of column. I know section modulus. Let us work out P and M. If you want to work out the axial force in the column approximately, I can say this weight is equally divided in two columns, though it may not be so, but approximately. I can take P is equal to W by T. So it is 23.375 kilograms. Roughly. 66.75 divided by 2. What's the bending moment? M. Yes. Bending moment M is 6 EI delta upon h square. And in this column it is 3 EI delta upon h square. I'll be taking the maximum of the two. 6 EI delta upon h square. Everything you know. What is delta? Max. We are calculated just now 1.24 something into 10 raised to minus 3 meters. Substitute and tell me the bending moment. Take everything in proper units. Yes, how much it is?
.654 into 10 to the power of 6.
Please check. E is 2 into 10 raised to 11.
Yes.
I is 2880 into 10 raised to minus 8.
Yes, sir.
Delta is 1.243 into 10 raised to minus 3 upon h square 4.57 square. Yes, Metapoli, what is the value?
2056.89.
How much?
2056.89.
Okay, 20.
56.89.
52.56.
56. 2056, sir. 6.
Okay,
.896.
2056.893 Newton meter is the value. And now substituting in equation 2. Let's call this equation 2. The maximum stress in the column is P by A. P you convert it in Newton. A is 100 centimeters square. So it is 100 into 10 raised to 2 mm square plus moment also you convert it in Newton mm. So 10 raised to 3 divided by Z 278 into 10 raised to 3. Convert that also in mm cube.
10.73. 10.736.
10 point.
Yes, sir.
Okay. Sigma is equal to 10.736 Newton per mm square or megapascal. And that is very, very small. Is it? Even if I take it's a steel column and laterally supported, the permissible bending stress is 165 megapascal. If I go by elastic method, it is very small. So this how this dynamic analysis is used to design the machine foundations. Got it? Okay. Well, what is the next point from the list I have given you?
Force transmitted to foundation.
So you can give that title, force transmitted to foundation. Force transmitted to foundation. See, one of the design criteria of this machine foundation that we are discussing for the reciprocating type of machine external force is F of T. Wall is also there. In the first design criteria, we have calculated maximum dynamic displacement. From that, we have calculated bending moment. From that, we have designed the columns. We have calculated axial force, bending moment, and then bending stress, axial stress in the earlier problem. Right? It's quite possible that the force that is transmitted to foundation, I will indicate it by F of T, is quite large, and this entire structure may move bodily as a rigid body. Quite possible, no? and we have to evaluate how much force is transmitted to foundation. And how will you ensure that your structure will not move? How will you ensure that your structure will not move? The force transmitted to foundation should be less than, who is resisting this? Force of friction. And that is due to normal reaction. So my design criteria is force transmitted to foundation should be less than the force of friction. With this objective or with this design criteria, we are studying this particular topic of force transmitted to foundation. You can take this figure, all of you, quickly. Now to calculate the force transmitted to foundation, let us consider the conceptual model. There is external force, then spring represent elastic force, piston and dashpot represent the damping forces. If I ask you, where is foundation in this conceptual model? Can you show me? Where is foundation in this conceptual model? Anybody online? If I can get that, I can find out what is the force transmitted to foundation. Here is the stiffness state, damping coefficient, columns are connected to foundation, damping force is also connected to the foundation. So, elastic force is connected to foundation, damping force is connected to foundation. This vertical line represents the supporting line. And force transmitted on this is the elastic force Ky and the damping force C by rho. These are the two forces that are directly transmitted to the foundation. External force is acting on the mass, not directly on the foundation. Inertia force is acting on the mass. So force transmitted to foundation is this plus this is the component. Quite easy. Agree? Okay. So I can write force transmitted to foundation is A1 plus C by 1. We call this equation 1. Where y is the dynamic displacement of the mass, is it not? Why is the displacement of the mass? So you can say where, why is the dynamic displacement of the mass? And yesterday we had derived equation for y, and we have said y is approximately equal to yp, and that is equal to e sine omega f t minus alpha. Let me call this as equation 2. Now, before I substitute this y in equation 1, let me find y dot. Find y dot. Take derivative of this equation 2. So derivative of equation 2 is e omega cos omega f t minus. Derivative of sin theta is cos theta. And this theta, I have to take derivative of this bracket further and multiply it. Now substituting these in equation 1. Substituting these in equation 1. Post transmitted to formation is A into B sine omega f t minus alpha plus C into E omega cos omega f t. Is it? Okay. If I want to simplify this equation, again I will use the same mathematical adjustments. If I want to convert it in sin A plus B, K and E are constants, so I can call this as G cos beta, where G and beta are some other constants. These two constants I am representing in the form of some other constant, and this I will represent as G sin beta. And now substitute and see what you get. Force transmitted to foundation. So G cos beta sin omega f t minus alpha plus G sin beta cos omega f t minus alpha. And now see whether you can write it as sin A plus B. You may take G common. If you take G common, it is G sin A omega f t minus alpha plus beta. Am I right? Okay. So this is the equation for force transmitted to foundation. You can say this is the equation for force transmitted to foundation. From this equation, it is easy for you to decide what is the maximum force transmitted to foundation. Ultimately, for design, I'm interested in maximum force transmitted to foundation point, Ft max, and this Ft max should be less than the force of friction. Then my structure will not slide. Stability against sliding, I'm checking. So what is the maximum force transmitted to foundation? G, then sin theta is maximum, is it not? So you can say, let's call this equation 3. From equation 3, the maximum force transmitted to foundation T max is equal to G. How will you calculate G? You have to work on these assumptions. G cos theta is A2 and G sin theta is C omega F. This is equation 4 and this is equation 5. Squaring and adding equation 4 and 5. You can say squaring and adding equation 4 and 5. So G is, we take E common, E into the root is required plus C omega square. Even I will take K square out. So E into K under root 1 plus, now it is C omega upon K square. Now taken K out. That is equal to E into K under root 1 plus C is R into CC. So R into CC is twice m omega into omega upon K is m omega square. All standard substitutions square. Same substitutions are repeated. So this m will get cancelled. Omega and omega square will get cancelled. Omega upon omega is small r. Finally, we will get G is equal to E into K under root 1 plus 2 RR square. Right? Now you may substitute value of E. E we are derived yesterday. It is F0 upon K into 1 upon under root 1 minus R square square plus 2 RR square. Substitute that. So maximum force transmitted to foundation, you will get F0 upon K and this K will get cancelled. So this F0 into under root 1 plus 2 RR square divided by under root 1 minus R square square plus 2 RR square. This is the equation for force transmitted to foundation. I can look at the equation of force transmitted to foundation, maximum force transmitted to foundation like this. F0 into some term, and that term is called transmissibility. So I can write this equation in short form as 50 max is equal to F0 into transmissibility. Where transmissibility is given by this bracket. You can say where transmissibility is equal to this. If I want to define transmissibility, I can define it like this. Transmissibility is Ft max upon F0. Maximum force transmitted to foundation divided by amplitude of external force. Right? So transmissibility is defined as the ratio of maximum force transmitted to foundation to the amplitude of external force exerted by the machine. The denominator of transmissibility is the magnification factor. Transmissibility depends on only two terms. One is capital R and one is small r. So you can say transmissibility depends on the damping ratio. In the bracket you can write capital R and the frequency ratio small r and the frequency ratio small r. Now, how transmissibility varies? We will plot the graph of transmissibility versus small r maybe tomorrow. We'll stop here for today. Yeah, number 1, Bhattad is there online? No. Number 2, Kurgaonkar?
Yes, sir. Present, sir.
Number 3, Satpute? Present? Okay. Number 4, Zinat? Okay. Number 5, Shirsi? Okay. 6, Bure?
Yes, sir. Present.
7, Wanjre?
Yes, sir.
Okay. Metapoli is here. Inamdar? No. Then Sayyid?
Yes, sir. Present.
Pawar? Bun? Sasne? Okay, we'll stop here.
For roll number 5 present.
For those it is possible for to come here physically, better come here instead of
Sir,
attending.
roll number 2 present.
Okay. System. That's right. Yes.